Good morning, everyone. Welcome back. So I'll just start off today with a couple of various announcements, information. So first bit of information is midterm 2 was graded. It was returned to you on the weekend. You probably saw that already. The midterm was fairly well done. Of course, not as well done as the first midterm. There was a bit of a dip in grades, but that's in some sense to be expected. We started to get into a little bit more abstract material. The average was 75%. I think you probably saw the stats for that. There was a lot of, I had a pleasure grading this because there was a lot of nice observations that people had and different ways to solve problems. So there's quite a variety, which showed off the stuff that you've learned in this course. That was nice to see. Sam's going to go over the details of the midterm questions and questions you may have on it tomorrow in tutorial. So that's announcement number 1. Announcement number 2 is the last assignment is posted, assignment number 9. And yes, that is the last assignment of the term. It's due on April 9th. So it's not due this Friday. This Friday's a holiday. Following Monday's a holiday. We got a long weekend this coming weekend. So I've just pushed the deadline back to April 9th, and that is the last assignment. What it's going to consist of, I've in some sense split it into 2 parts. You don't have to worry about the parts other than just to compartmentalize the information. Part 1 just focuses on chapter 17 and 18. In other words, equivalence, relations, and cosets. So that's this first page, questions 1 through 5. Question 6 is back to the oval track. I'll talk about that in a second. So questions 1, 2, 3, 4, and 5 are about chapter 17, 18 materials, so equivalence, relations, and some cosets as well. And I'll come back to question number 6 and mention that in a second. Part 2 is going to be on the fundamental theorem of cubology, or the fundamental theorem of Rubik's Cube. And so that's chapter 20. And we'll get into this material today. So if you're looking at this going, I don't know how to do that, that's perfectly all right, because we'll get into this today. We'll figure out how to answer these questions today and Wednesday. And by the end of Wednesday, you'll have all the information you need to answer questions in the second part. There was this question that I also put in on the first part because I thought it was an interesting question. So this question comes back to the oval track and is just purely a question about, is it possible to flip the turntable? And so what does that mean? It means the turntable is flipped over. So can I find a sequence that moves tau so that the turntable has changed orientation? So now it's flipped over, but all of the tiles, all the discs are back where they started from. So this was a move sequence that was an identity on the discs themselves, but it actually ended up resulting in flipping the turntable. And this question asks you to actually find such a move sequence. So this is more of an exploration type question where you got to have some strategy. You got to have some strategy as to how you're going to look for this move sequence. In other words, it's got to use the turntable an odd number of times to end up flipping it in the end. So you got to look for moves that effectively are the identity on the discs, but flip the turntable. So that's more of an exploration. By all means, get a group of you together, start exploring these things, chat with other people in the class, make this a bit of a social question. I'd be encouraging you to do that because it is an interesting question. Because what it really boils down to is it says that in all the pictures I've drawn in the textbook, I never showed the turntable upside down, or whatever the starting configuration was, the turntable was always right side up. And this answers the question of, does the turntable depend on the permutation? And the answer is no, because the turntable can be moved independently of the permutation of the pieces. So this just sort of answers some subtle questions about the oval track puzzle. Okay, so that was announcement number 2, last assignment number 9, which is, cause for celebration. The last one, sorry, I'm just looking at the chat here. The tongue twisting here. Will our lowest assignment be dropped? Yeah, I'll drop the lowest assignment. So everyone has a bad week, a bad day, etc. I don't want that to impact your grade. So yeah, I'll definitely be dropping the lowest of the 9 assignments. So the lowest score. I'll normalize all the scores and then pick the lowest one. Normalizing meaning I'll just make them all out of the same thing for the purposes of dropping. So I'll drop the assignment with the lowest percentage. The previous question in the chat was, will our project presentations be officially, when will they start? So the idea is our last assignment is due on the 9th, and then the following week is presentation week. Presentation week will consist of the classes on Monday, Wednesday, and probably Friday, but it will also involve the 2 tutorial time slots as well. That will allow us enough time to get all the presentations in. So I will be posting within the next day or two a schedule, basically asking you, do you want to sign up for the Monday, Tuesday, Wednesday, or Friday slot? I will hopefully try to get everyone in on the Monday, Tuesday, Wednesday. So I'm going to reserve the Friday slot as sort of a backup slot. But the Monday, Tuesday, Wednesday will be our 3 days. Presentation. Oh, does it say something on Canvas? There's probably something left over from a previous term. Yeah, so the present, once we've identified the time slots, then that's really it. It's just come on presentation day. How will our peers be evaluating that? So that will be announced as well. You'll be a peer assessments. And so I'll announce the details of that too. But for right now, it's just I'm going to make the calendar available for slots to sign up in. And so you just want to decide whether you want a Monday, Tuesday, or Wednesday slot. All right, so that's the announcement about the project, and that takes us through the last week of the course, and that's pretty much it. So we're in the final stretch here, pretty much. So let's get into chapter. Oh yeah, maybe I should mention that for the final project presentations, everyone you'll be given basically a 10-minute time slot, and that 10 minutes you'll have to present. You don't have to fill the whole 10-minute time slot. I'm not saying you got to go right to the last minute. No, it's just if you've created a video and it's a 5-minute long video, then it's 5 minutes long. You can field some questions and answers, or you wrap up early. If it's a website that you've created or an applet and you can demo it, you've got up to 10 minutes to do that. All right, let's get into today's topic. Today's topic is really bringing everything that we've developed over the course all together in what we're calling the fundamental theorem of cubology. So this, so will the standards be higher if we present on a later day, since we have more time? There's not too much more time. We're looking at Monday, Tuesday, Wednesday. But no, it's, well, you're encouraged to go early, because when you do go early, of course, the graders, Sam and myself, are a little bit more appreciative of the fact that you've gone early. So I'll leave that sort of as stated as such. So what we're doing with the fundamental theorem of cubology is we're really now doing a solvability criteria analysis for the cube. So let's just back up for a second and go to what we've done on the Rubik's Cube itself. So what we've done on the Rubik's Cube itself is we've cataloged a collection of useful moves. And let me just scroll down. Here we go. So here's our collection of moves, 4 moves that are all we need to know in order to solve the cube. We need to know how to 3-cycle corners and 3-cycle edges. That's 4A and 5A. Corner 3-cycling, edge 3-cycling. Both of those are commutators. So the corner 3-cycling is the commutator listed on the first row. The edge 3-cycle is the commutator listed in the third row. Once we've 3-cycled, that effectively allows us to position any piece in the right location. So we can actually put all the pieces in their right locations. It's just we haven't twisted or flipped them to the correct orientation. But that's for the other 2 moves, the orientation moves. Corner orientation moves, we can rotate 2 corner pieces in opposite directions, 1 click, essentially. And 5B is we can orient 2 edge pieces by flipping 2 of them at the same time. So double edge flip or a double corner twist is really what I refer to these as. So we got the ability to do 3-cycle corners, 3-cycle edges, double corner twist, or double edge flip. And all of these were built as commutators. We can modify them so that if we don't want 2 edges flipped that are adjacent to each other, maybe we want them to be opposite each other on the puzzle, we can just do a conjugate of that. Bring the edge pieces we want to flip into those 2 positions in the figure in the bottom, flip them, and then undo the setup move, undo that move that brought them into those positions. And so through conjugation, we can take this double edge flip and make it flip any 2 edges we want. Similarly for the corner twists. So these are the only 4 moves you need to know on the Rubik's Cube. Now, we haven't proven this, right? I haven't shown you that 3 cycling is all you need to know how to do for corners, and 3 cycling is all you need to know how to do for edges. And twisting 2 corners in opposite directions is all you need to know for orientation. So we still need to prove that. And that's chapter 20. Chapter 20 says, hey, you've played around with the cube enough. Anytime you've solved it, these 4 moves were really all you needed. Was that just pure luck? Or is there an underlying result that says that, no, actually, these are the only 4 moves you'll ever need on the Rubik's Cube? And chapter 20 says, yeah, these are the only 4 moves you'll ever need. And that's what we're going to get through now. In fact, we'll get through more than that. We'll get through not only are these the only 4 moves you need to solve the cube, we're going to investigate the solvability criteria. So what configurations of the cube are solvable, what ones are unsolvable, and the like. And so what we're going to do, because the Rubik's Cube is a spatial puzzle, we can hold it in all sorts of different orientations and positions, that we just want to come up with a standard orientation. So this is the top, this is the front face, and we will reference the position of any piece relative to those. So this is our standard orientation: blue up top, red in the front. And because we're looking at a standard cube, because blue's on top, green is always opposite blue, so green's on the bottom. Orange is always opposite red, so orange is in the back. And there's always this, if you are standing on the blue face and you walk sort of clockwise around the corner that joins the blue and the red face, the yellow is a part of that corner as well. So yellow is always going to sit on the right-hand side if blue is up top and red is in the front. That's just the standard Rubik's Cube stickering pattern. You can buy other cubes which have non-standard coloring schemes, but we're going to go with the standard one here. If you have a non-standard one, then you just update your color, pick an orientation and make it your standard one. It doesn't really matter that blue's up top and red's in front and yellow's on the right, other than the fact that we're just going to be basing all of our labeling off of that. But just pick a standard orientation for your cube and label it accordingly. So then what we do is, once we've got our standard orientation, then we're going to define a configuration of the cube. So we mixed it all up. A configuration is going to be defined by the permutation of the corner cubies. So where do those corner cubies go? That's row. And since there's 8 cubies, 8 corner cubies, row is an element of the symmetric group on 8 objects. Sigma is how the edge cubies got permuted. So the edge cubies, we're not talking about orientation here. We're just like this, for example, this edge cubie in the front, oh, it got moved over here into the edge cubie that's in the right down layer. So that edge cubie. So that just means that edge cubie up top went to where the edge cubie, the position down in the bottom right. I don't care about orientation. This row and this sigma does not care about whether these things have been flipped or twisted if they're corners. All it cares about is where did the whole cube go, the whole QB. Where did that small little QB go? So that's row and sigma. And then V and W are where we encode orientations. So V is going to be a vector, that's why I've got a little arrow on top, and it's going to encode the orientation of the corner cubies. So this is a vector with 8 slots in it because there are 8 corners, and so V is going to be a vector with 8 slots or 8 positions that we're going to fill it up with. And W is going to be a vector with 12 slots, 12 components. How are we going to fill it up? Well, since for a corner cubie, there's going to be 3 different ways when you take a corner cubie and you're going to put it into a location that it resides, there's going to be 3 different ways to orient it. You can twist it in sort of 1 click, 2 click, or no clicks. And so this would be a number in each of these components that's either 0, 1, or 2, but we'll get to the details of that in a second. And same with W. W's for each edge cubie, it's either flipped or not flipped. So it's going to be a 0, 1. So how can we think of them as vectors? We're actually going to, so we're going to do one thing where we're thinking of them as vectors. This is just a list. It's just going to be a list of 8 numbers or 12 numbers, depending on whether it's the corners or the edges. Later on in chapter 21, which is a shorter chapter, we can think of them as vectors as in the group operation turns out to involve addition, component-wise addition on these things. So it's going to be vector addition. So that's another way we're going to think about them as vectors. But for right now, you can think of them as just lists. They're just lists of numbers. So we'll get some examples. Okay, so to talk about permutations of the corners and the edges, I've drawn 2 different diagrams here. The one on the left has labeled the corners. And again, remember, we've got our standard orientation. So this is a blue centerpiece here. This is a red one in front. This is our red centerpiece here. And this is our yellow centerpiece over here. So that's our standard orientation. And that's how we're going to label the corners. The one in the left back up position is corner number 1. And then we just go sort of clockwise around that up face. Corner number 2 is in the up back right position. Corner number 3, corner number 4, and then we go down to the bottom layer and wrap around it. So those are our corner labelings. And so you want to be able to think of things like this, like what does corner piece 1 look like? Well, corner piece 1, if I draw a little corner cubie, so I've removed this little tiny cubie from the puzzle, and it's a corner cubie, so I'm going to look at the colors that make it up. Then there's going to be a blue color on one of the sides. So that's, I'm going to draw it this way, it's the upside. But now I imagine looking at that corner piece, so I'll grab one, and I imagine looking at that corner piece. So if you're holding it with the standard orientation, and we're going to look at that corner piece, which is this one back here. So then I'll angle it so you can stare at it. Let's see, there it is. There's that corner piece. So there's a blue color, white color, and an orange color wrapping around that corner piece. So this is a blue, a white, and an orange piece. So this is corner cubie number 1. Corner cubie number 1 is the corner cubie that has the blue sticker, the white sticker, and the orange sticker on it. That's corner cubie number 1. And that's its location where it sits, its home location in the diagram. And then we can think, what's corner cubie number 2? Well, that's got to have a blue sticker. It's got to have a sticker which is the same color as what's on the back. That's also orange. So it's got to have a blue, an orange, and it's got to have a yellow sticker on it. So corner cubie number 2, we'll just draw another picture. Corner cubie number 2 is this one over here. And that corner cubie is going to have a blue on top. It's going to have an orange on one side, and it's going to have a yellow on another side. So that's corner cubie number 2. And so it's important to know how to identify these corner cubies by just looking at these diagrams, because we're going to want to be able to find where they went to on the puzzle when we're looking at the permutation that we've got. Similarly for the edge QBs, we've got, edge QB. And for the edge QB, there's only going to be two sides, so I'll just shade in. That's going to be something that you don't get to see. You don't get to see all of the sides. You only see two of them as an edge QB. There's going to be a color sticker on one side, and then there'll also be a colored sticker on the other side. In this case, the edge QB that goes in slot number 1 is the blue-orange edge QB. So that's edge QB number 1. And for example, edge QB number 2 is going to be the one that looks like it's going to have a blue sticker, and it's also going to have a yellow sticker on it. So that's edge QB number 2. That's the one that's going to go right here. Okay, so that's what we're labeling. We're labeling the positions on this puzzle, and we're also making a note of what is the QB that goes there. So then when we mess up the puzzle, the corners have moved around. And so we're going to identify the corners by their corresponding permutation. And that's going to be a permutation of the corners 1 through 8, and the edges will have moved around. So that will be a permutation of the numbers 1 through 12. So now we want to get into orientation. Well, maybe I'll do one thing first before we get into orientation, just so you get a feel for what's happening here. I will bring over into the window Rubik's Cube. And we'll just, do a few moves to sort of mess this thing up a little bit. And maybe something like that. There we go. Okay, so if I want to figure out what the permutation is on the corners, I have to put it into its standard orientation. That's blue up top. So I look at the centerpiece, blue's up top. This is the red face, it's out front. This is the yellow face, it's to the right. And now I want to know, where did the corner piece from position 1 go? The corner piece from position 1, I can glance up at my diagram I've done here. This is a blue, I always read them clockwise around the corner. So this is the blue, white, orange corner piece. So I scan around my puzzle and I try to find the blue, white, orange corner piece. Blue, white, orange, where are you? Oh, there it is. So it's right here. So when I move it back to my standard orientation, that's my blue, white, orange corner piece. So the corner piece from position 1 is now in position 2. Where did the corner piece in position 2 go? Corner piece in position 2 would be the blue, orange, yellow corner piece. So where did blue, orange, yellow go? Oh, I see a blue, orange, yellow down here. So this one right here, just angle it up a bit. There it is, blue, orange, yellow. So it's right here in the front face on the left side in the down position. So it's right here. So corner piece 1 went to corner piece 2, and now we've just seen that corner piece 2 has now ended up in position, let's go back to our diagram behind, position 8. So 1 has gone to 2, 2 has gone to 8, and so on. So we're using that coloring scheme to be able to identify which corner number it is, and then figuring out where that number went to. Where did that corner piece go to? And so that's how we construct this permutation row. And similarly for the edges, we would do that to get the permutation sigma. So our edge piece number 1 is blue, orange. So that's supposed to be the one that starts back here. That's the corner position or edge position 1. So where is blue, orange? I scan around the puzzle. Blue, orange. Oh, it's probably down. There it is. So there's the blue, orange piece. Now I'll put it back to proper orientation, just keeping an eye on where it is. So it started here, position 1, and it ended up down here in position 12. So I'm looking at my diagram. That's position 12. So 1 has gone to 12. And then similarly for the other edge pieces. This is how we track where pieces have moved from and where they moved to. Once they get there, once the piece gets there, so let's just follow that first corner piece. Corner piece started here, corner piece 1, and it's ended here. So corner piece 1 is now sitting in this position. And now I want to attach a value to that that says, okay, it's 1's gone to 2 for the corner permutation, but now that corner piece 1 has what orientation? Well, I need to decide how I want to encode the orientation information, because blue could be on the side, or I could rotate this 1 click so that blue is on the top, or I could rotate it 1 click so that blue is on the back. So there's 3 different ways for this corner piece. Once I know where it is, there's 3 different ways for it to be oriented there. And the idea is we got a corner piece, and let's see if these ones twist. They do. So it could be oriented like that, or it could be oriented like that, or it could be oriented like that. So once we get it there, there's 3 different ways to orient it. And now we need to encode that information as well. And that's where those vectors come into play, the V and the W vectors. So that's this next little bit. How do we talk about the orientation? Well, again, with orientation, we're going to have some frame of reference. So what we're going to do is we're going to choose a primary sticker or a primary faucet for each cubicle. Now, the way I'm using this terminology is sticker is a piece on the QB that moves around the puzzle. A faucet is the location in space that the sticker slides into. So it's like the home position for this, or the position a sticker can reside in. It's like this fictitious layer of skin that sort of surrounds the puzzle, and it's got these little spots where the stickers can slide in and out of. Faucets don't move. Stickers do. Stickers move around the puzzle. The faucets do not. So typically in other puzzles, we've referred to these as positions, like the oval track, the position 5, position 7 versus disc 5, disc 7. The analogy here is we're using the faucet to denote the position, and we're going to use the word sticker for the actual piece that moves around, as well as the QB itself. It's also a QB is moving around. So it's either we're looking at the whole thing moving, the QB, or the individual sticker, depending on whether we're talking about orientation or piece. So with a QB, those are the pieces that move around. Where they sit in are the cubicles. So cubicle, faucet, those are positions that QBs and stickers can land in. So what we're going to do is we're going to choose a primary faucet. This is the location that a sticker can reside in for each cubicle, the locations that each QB can live in. And we're going to mark it with a plus sign. And so what that does is it sets of all of the faucets that the stickers can land in for a given cubicle, we're going to take one of them as like the primary one. It's the one where we're going to build our frame of reference from. And so we imagine a thin layer of skin sort of all around the puzzle, and we're just marking a little plus sign on this outer layer. So I'm going to show you what this will look like, only there's a problem with this in that this little plus sign, I want to be just hovering above that sticker position. The problem with how I've got it right now is those plus signs move. This is not what we want. Those plus signs are fixed in space. They're hovering above where this sticker is, so that whenever I have a corner piece that lands in this position, I can talk about its orientation relative to the little plus sign that's hovering above the sticker that's in the up layer for that corner piece. So these pluses are just hovering above the stickers. They're the skin. If you want to think about an analogy, these plus signs are really just markings on these numbers that are hovering above the places that the discs can sit. So 2, 3, 4, 5, 6, 7. Those are the positions, or for lack of a better term, if we're drawing an analogy here, those are the faucets, whereas these discs are like our QBs. the location the disc can sit in is like the cubicle. And the plus sign is a marking that's on these positions. Now I don't need a plus sign here because there's no orientation. Once a disc is there, there's no upside down for the disc. So we don't need to have orientations, but now we do. Okay, so that's how we're going to identify a primary faucet, a primary face to build our location for a sticker to build our orientation off of. What we do on the stickers themselves, however, is when the puzzle's in its solved state, then what we're going to do is we're going to number the stickers themselves based on where they sit in relation to their primary faucet. So for this corner piece, it's in its home location. Blue is the sticker that's underneath the marking plus. So blue is in the primary faucet. So I would number that 0. I'm numbering that sticker 0. It's 0, you can think of it 0 clicks away from the primary faucet, or it's the 0th sticker. It's sitting in the primary faucet. And then we just number things going around in a clockwise direction. So this is 0. This yellow piece would be number 1, or yellow sticker would be number 1, and the red would be number 2. On the other hand, for an edge piece, the sticker that resides in the primary faucet in its home position is sticker number 0, and the opposite one is sticker number 1. So we're going to get numberings that look like this: 0, 1, 2, 0, 1, 0, 1, and then I just scroll around. 0 because there's a marking there, a plus sign was there, and then 0, 1, 2. So that's giving us a way to number all of these stickers so that we know what is the primary sticker for that corner or edge piece and whether it's in the primary faucet wherever it's gone. So I'm just going to scramble this up a little bit, and we'll look at let's see. Okay, this is good because I actually wanted corner piece number 1, which was back here, to land out front so that I don't have to really change around the orientation. So there's a scrambled version of the puzzle. This blue, white, orange corner piece, that's corner piece number 1. And we're seeing that corner piece number 1 has gone from here to here. So for the permutation corner piece or the permutation row, 1 has gone to 3. So that would be where we'd record in row. Okay, 1's gone to 3. I know where the corner piece has gone to. Now I have to record, how is it oriented there? Well, what I do is I look at the corner piece and I see which sticker is in the primary faucet of that location it's now sitting in. And it might help to reference the primary faucet labelings. So let's get that in the image as well. So these are our primary faucet labelings. So we're currently sitting in corner cubicle number 3. For that cubicle, the sticker that's in the up layer is the one that's in the primary faucet. That's the location that we're calling primary. And I just record what is the number that's in that primary faucet. So for here, it's number 2. Number 2 is in the primary faucet. So if I said corner piece 1 has gone to cubicle 3, and it's oriented with 2 in the primary faucet, then you know exactly where to put it and how to rotate it before you jam it into place. You have to make sure that the sticker with the 2 on it is in that primary faucet. So we'd record the number 2 for that corner piece. That tells us how it's oriented. If the 1 was up here, so let me just rotate it again. Okay, so there it is. This is, again, the corner piece is now in position 3, but now it's a 1 that's in the primary faucet. Or here it is where the corner piece has gone from 1 to 3, but now it's a 0 that's in the primary faucet. So we need to record where it went and what is the number on the sticker that is now in the primary faucet. Now, of course, your puzzle isn't oriented with these stickers. Or sorry, your puzzle isn't, it doesn't have these stickers on it. You're playing with an actual puzzle. It doesn't have these stickers on it. So how would we do that in practice? Well, I'd go blue, white, orange. That's corner piece 1. It's now sitting in position 3. What is the orientation? Well, I know that it came from position 1. Position 1, the up sticker was in the primary faucet, so that's sticker number 0. So I know blue is going to be 0. In fact, a little hint, all the blues are all zeros. I mean, we get that. That's why I've labeled it this way. Anything that's touching the up layer as a sticker is getting a 0 on it. So all the blues are 0. And looking at the down layer, all the green stickers are zeros. Then that leaves only 4 around the belt that are edges, which don't have a blue or a green sticker on them. So those ones, if they don't have a blue or a green, then these pluses are on the yellow side. So for the yellow-red edge piece, yellow's the 0 or the primary sticker. And for the yellow-orange one, yellow is again the primary. So yellow is getting the zeros, or whites are getting the zeros for these 2 edges. So it's sort of the hierarchy is, if you've got a blue piece on it, that's a 0. If you've got a green piece on it, that's a 0. If you don't have a blue or a green piece on it, then the yellow or the white is a 0. And you never get a yellow-white on a single piece, so there's no ambiguity there. If there's no blue or green sticker on it, then the white or the yellow is the 0. So then when I look at this piece, I'm like, okay, it's got a blue sticker on it. That's a 0. And then I just run clockwise around. 0, 1, 2. So 2 is in the primary faucet. So corner piece 1 went to position 3, and 2 is the number on it. Let's do it for another one. So this corner piece back here would have been the blue. I shouldn't really have to twist this anymore now that we're getting familiar with the color scheme. Blue opposite red is orange. So this corner piece is the blue, orange, yellow one. And I look around my puzzle and I see blue, orange, yellow is there. So corner piece 2 has gone to position 4. And what's the orientation number associated with it? Well, I know this is a 0 on the blue face. So that's 0, 1, 2. So the orientation number would have been a 2, because that tells me that the sticker with the 2 on it's got to be sitting in the primary faucet or touching the up layer. So that's how we're going to do these, and we'll get some more practice. I'll just go through the last little bits of the definition. So that's how we're going to label these: 0, 1s, 2s for all the edges, 0, 1, 2s for all the corners, 0 and 1s for all the edges. Anything that's got a blue sticker on it is a 0. Anything that's got a green sticker on it, the green sticker is a 0. If they don't have a blue or a green, it's the yellow or whites that are going to be the zeros. And you get the other ones by going clockwise around the vertex, or in terms of the edge, it's just the other sticker is the 1. It also helps in knowing that, you know, it's only the ups that get the pluses and the bottom and the downs that get the pluses, and then the rights and the lefts. Those are the primary faucets coming from this picture over here. Because once we get to a particular location, we need to know, you know, where's the primary faucet. So the primary faucets are always in the up layer or the down layer, or in that case of the middle belt, it's the right and left sides. This labeling is completely arbitrary. All I did was say for each corner cubicle, I pick one faucet that's the primary one. And I do that for all the edges as well. It's completely arbitrary. You just have to pick one of the 3 for every corner piece. This labeling we've chosen because it's easier to remember. Up, down, those are all pluses, right and left for the belt. That's the only reason we're doing this labeling, is it's easy to remember. You might want to modify this labeling if you want to answer other questions on the puzzle. There's people have modified it to answer different questions on the Rubik's Cube. Based on solvability criteria. This one is the one we're going to use because it's just easy to remember, or easier to remember. Okay, so this brings us to our, puzzle to permutation kind of step that we did back in, I think it was chapter 5 for our flat type puzzles, where we took our puzzle configuration and mapped it to a permutation. Only with the Rubik's Cube, it's puzzle to 2 permutations and 2 vectors. So there's a 4 tuple, which we're encoding the position of the Rubik's Cube. The first permutation is that row permutation. It's how the corners are moved, and that's just our regular, how things got permuted. Corner piece in position I went to position J, so I goes to J. Sigma is our permutation for our edges. Sigma I goes to J if the edge piece from position I is now in position J. What about our orientation vectors? So for the corners, these are going to be 8 different numbers. Each number is just so I'm reading now the right-hand side. So each number, say VI, is the number on the ith corner QB. So first figure out where the ith corner QB is. You got to find it on the puzzle, and you've already done that by your permutation row. Now you know where the corner QB is. Then you look at which numbered sticker is underneath the primary faucet, underneath the plus mark, and you just record that number down. So it's either going to be a 0, 1, or a 2. So that's why each of these VIs is a 0, 1, or 2. And same with the edges. Same thing with the edges. Where did the edge piece go? Once you figured out where it is, which edge sticker is in the primary faucet? Is it a 0 or is it a 1? And we just record that. And so this would be a vector of 0s or 1s. So vector, in this case, we're just meaning either an 8 tuple or a 12 tuple, but later on we'll see that you can actually do linear algebra with these things. You can do additions and the like. Okay, so we won't get into that right away. Right now, we'll just think of them as lists. That's really all we need. It's just a list of orientation numbers. So let's go ahead and do some encoding. So determine the position vectors for each of the following configurations. So we're going to write down, so the position vectors. So in this case, the position vector, so it's that whole 4 tuple. That's what we're calling the position vector. It's a 4 tuple. So it's a sort of dual use of the word vector. Here we're thinking of vector now, where the first component is a permutation, the second component is a permutation, and the third and fourth components are these lists, or subsequently more vectors. So what we need to do is we need to find out row, we need to find out what sigma is, we need to figure out what V is, and we need to figure out what W is. So what is row in this case? How have the corner QBs been moved around? What is row? So feel free to answer in the chat. So what is row? Where did corner piece 1 go? Where did corner piece 2 go? Yeah, you got it. It's the identity. Corner piece 1 is still in position 1. Corner piece 2 is still in position 2. So that's the identity. Similarly for sigma, edges haven't gone anywhere. So that's our position, our permutation. Sigma is just the identity. How about V? What are the orientation numbers? So there's going to be, this is for the corners, so there's going to be 12 of them. A long list of them. And then, 8 of them for the corners, and then 12 of them for the edges. So what are these? Yeah, 0 vectors, exactly. They're all right where they started. 0 was the sticker, the number on the sticker that's in the primary faucet. All of those stickers are still in their primary faucets, so it's zeros all the way down. 4, 5, 6, 7, 8. Or in other words, it's the 0 vector, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, or the 0 vector. So the solved state is encoded by identity, identity, 0, 0 vector. That's our 4-tuple for the solved state configuration. So let's go ahead and look at the next one. We've done a move R, or R inverse in this case, a counterclockwise rotation of the right phase. Let's figure out what rho is. So 1, corner QB1 hasn't gone anywhere. It's still where it is. Where did corner QB2 go? What position did it land in? Corner QB2 went to what position? Yep, went to position 3. So 2 went to 3. Where did 3 go to? So 2 went to 3. 3 is rotated around. It's now in, yeah, you got it. 2, 3, yeah, there you go, the whole thing. 2 goes to 3, 3 goes to 7, 7 went to 6, 6 came back around again to position 2. And this reflects the fact that doing an R inverse move is a 4 cycle on the corners. What about sigma? So for sigma, I haven't even put the labels on the locations for the edges, because otherwise the diagram just gets really really cumbersome. It's really cluttered. So for the corners, or so for the edges, we can just, I mean, even if you're holding the puzzle, then you don't even have numbers at all floating around. But we just have to try to remember what they are. So I'll scroll back and just get a bit of a starter for this. For the edges, we start with 1 out in the back, and we just go clockwise and we just sort of cycle our way around. 1, 2, 3, 4, drop down, back left in the middle layer is 5, 6, 7, 8 around, and then drop into the back layer, and that's 9, 10, and 11 and 12 finishing out front. So, or out to the right. So this is corner piece, this is corner position 2 here, and then we'd have a 3 up, or edge position 3, and then 3 is in the front, 4 is out here, and then 5's in the back middle. This one is 6 here, this is 7, then we get 8 and 9 in the middle, and then 10 in the back, and then this would be 11, and this would be 12. So just getting a feel for where these numbers should sit. So what is sigma? Sigma takes, so it doesn't affect 1, it takes 2 and goes to position 7 with it. So edge 2 has gone to position 7. 7 has gone to 11. 11 has gone to 6, and 6 has gone to 2. So there's our, I'm just checking here, 11. Oh, yeah, that wasn't 11, that was 10 down here. My mistake. 10, 11, 12. Good thing I'd glanced over it. That's actually a 10. 9's in the back, 9's in the bottom back, and 10's out on the right. So that should be a 10 there. All right, and now we've got to get our orientation vector. So this is how things are oriented. The first entry is the orientation of corner QB1. It's back in its proper spot. It hasn't even been rotated at all, so it's a 0. So I look at that corner QB1, which is sitting in position 1. The blue sticker is still in the up face. Corner piece 2. So rho tells me that's now in position 3. So I glance over at position 3. I'll zoom in a little bit. Glance over at position 3. I know that this is going to have a marking of 0 on it. And then I run around in the clockwise direction. So those would be by sticker numbering, 0, 1, 2. 1 is the labeling on the sticker that's in the up layer in the primary faucet. So that means that this is going to be a 1. corner QB2, in the location it now sits in, it's the sticker with label 1 that's under the primary faucet. So that's my orientation. How about corner piece 3? Corner piece 3 is now in position 7. I get that from that row. So I'm looking down at position 7. That's a 0, that's a 1, that's a 2. And so 2 is the number that's in the primary faucet. So that's a 2 there. What about corner 4? Well, it didn't move anywhere, so that's still a 0. 4 is a 0. 5 hasn't gone anywhere. That's still a 0. 6 has gone to 2. So 6 is in position 2. I look up there and I see there's a green sticker on it. So that would have been 0, going clockwise around. 1, 2. 2 is the label on the sticker that's in the primary faucet. So that's going to be a 2 there. So that's 6. 7. Piece 7 is now in position 6. So that's down in the bottom right corner. So I'm just going to circle the pieces that make up. That's that corner piece that's now sitting in position 6. So that's corner piece 7. And so I'm going to label those. We've got a 0 on the one on the green sticker. And then when I read clockwise around it, this would be a 0, and then the bottom would get the 1, and then the side would get the 2. And so it's the 1 that's in the down face. So that's the label that's in the primary faucet. So that is corner 7. Corner 8 is back where it started, and it hasn't been rotated. So that has a 0 there. So that gives us our vector for the corners. Then we do the same thing for the edges. Even though there's more edges, they're a little bit simpler. They're a little bit simpler because it's either a 0 or a 1. So I'll do this quickly because I see we're out of time. So 1. Edge piece 1 hasn't gone anywhere, and it's back where it's supposed to be with the right orientation. 2 has gone to 7. So if I look at position 7, edge piece 7, it's the blue, yellow one. Blue would get the labeling 0. 1 would be the other face, and that would be the primary faucet. So that gives us a 1 there. And then what about 3? 3 hasn't gone anywhere, so it's proper oriented, so it's 0. 4, that hasn't gone anywhere. 5 is in the middle belt in the back, hasn't gone anywhere. 6 has gone to position 2, so it's up there in the top and the up right face. It's an edge piece that doesn't have any blue or green, so I know 0 is the yellow and 1 is that one there. And so the 1 is on the orange sticker, which is in the up face now, which is the primary faucet. So that's a 1. So that's 3, 4, 5, 6. That's 6. Then what about 7? Edge piece 7 is now in position 10. And edge piece 7 is one of these belt ones. So it's the yellow sticker that has the 1 on it, or 0 on it, sorry. So red has the 1, and 1's in the down face. So we get a 1 there. So that's 7. And then 8 is a 0 because it hasn't gone anywhere. 9 is a 0. It hasn't gone anywhere. 10 has gone to position 6. So I'll circle position 6. It's made up of these 2 pieces. And it's the green sticker that has the 0 on it. So this one has a 1, and that means the 1 is in that position. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 11 and 12 are back where they started with 0s. And so there is the encoding of this R inverse move. And that tells us complete information, where all the pieces are, and how they're oriented. So these are like assembly instructions. This is how you'd reassemble the cube into this form by just knowing where each cube goes, which cubicle, and then how to orient it once it gets there. So we'll do this move U and the subsequent move next day. And then we're going to observe that there are certain patterns that these rho sigmas, V's, and W's satisfy. And those patterns they satisfy are going to be the solvability criteria. So I'll stop there.